One of the things we were talking about last class, or last video, however you want to look at it, was this idea of stoichiometry and using it when reactions do not go to completion. So this is the idea of the percent yield. When you have reactions, the assumption with the stoichiometry, the chemical reaction, is that the reaction proceeds to completion and all the products are formed in the correct amounts. But in reality, there's often loss, either through physical loss or competing reactions that lead to alternate products. There's another problem that you deal with in the real world, and that is when you do not have enough reactants. So we talked about the product side in the terms of the yield. So let's talk about the reactant side, limiting reagents. Oh, coffee! We looked at the product side. Now let's look at the reactant side, where we look at the situation where we do not necessarily have enough reagents to proceed in the manner that we would like. We've already seen this, okay? Back at the beginning of week 2, we were dealing with coins. And in those lectures, we had to predict how many sets we were going to make. And we did this by predicting how much product we could form and using each of those individual reagents. If we know how much we have, we can predict how much product is going to be formed. In the real world, though, we can be limited by how much starting material we have. And these are what we call limiting reagent problems. It isn't always possible to combine enough reagents in the right stoichiometry, or we mix two things together and we only can really control the amount of one of them. And what happens is this limits how much product we can form. Now, limiting reagent is one name. I myself like to call them cake problems, because they're pieces of cake. So, all limiting reagent problems are actually multiple steps, at least 2 steps. And what you have to deal with is, again, that problem before the problem. I mean, you want the answer, but you have to set up the situation so you can get to the end problem. So let's take a quick look at one, and we'll do, again, cake problems, because we can use cake as an example, though coins is one we did earlier. So we have 12 eggs. We want to bake a cake. And so we have 2 eggs, 3 cups of flour. We'll make 1 cake. Right? We can think of this as a chemical equation. 2 eggs, 3 flour. Right. So if we have 12 eggs and 12 cups of flour, the question is, how many cakes can you make? Well, using the 12 eggs, we know that for every 2 eggs, that is equivalent to 1 cake, giving us the ability to make 6 cakes. Alright, not bad. We can do the same calculation with cups, and we see that for every 3 cups, that gives us 1 cake, allowing us to make 4 cakes. So, how many cakes can we make? Well, that's easy. 4 cakes, right? 12 eggs, 12 cups of flour, we can make 4 cakes. Additionally, what this means is we are limited by the amount of flour. the flour limits how many cakes are made. The reagent that limits how much product we can make is called the limiting reagent. Not surprising. If we have a stoichiometric amount of reagents, if we have exactly enough eggs to use up all the flour, there's no limiting reagent. But any other time, one of the reagents will be limiting. It will limit how much product you make. The other reagent, in this case, is the excess reagent. And as the name implies, it is present in excess. The question is, how much excess? How much is left over? Well, to figure out how much is left over, we can start with our limiting reagent and predict how much is left over. With limiting reagent problems, the trick is always use the limiting reagent as the starting point, regardless of what the question is asking. The question could be asking about cakes, the question could be asking about something else. But to answer the question, in this case, we answer the question during the solution of the problem, during the determination of the limiting reagent. But finding the limiting reagent is not always the answer. This same question could have been asked, if I mix 12 eggs and 12 cups of flour, what and how much is going to be left over? So if we know the limiting reagent is the flour, then we can use the limiting reagent, the 12 cups of flour, to predict how many eggs are left over. We know that for every 3 cups, that's equivalent to 2 eggs. That we will utilize 8 eggs. Here's a trick. Write down what those 8 eggs are. 8 eggs are used. If we were asked how much was left, it's not 8 eggs. It's the 12 eggs you start with minus the 8 eggs you use will equal 4 extra eggs. So, the limiting reagent problems. When you see a limiting reagent problem, you find the limiting reagent, and then you use the limiting reagent to answer the problem. So the method I laid out for you was what I like to call the starting material method, where you use each of the starting materials, 12 eggs, 12 cups, and then you push everything to the products. And in this case, one that gives you the least product is the limiting reagent. Again, we can see that from our example. The cake example says that 4 cakes can be made with 12 cups. We are limited to 4. Can't make more than you have. This is a useful method when your question is asking you about how much product, which it may also be asking you about yield, theoretical yield. Just because you see yield doesn't mean it's a percent yield problem. All right? If they ask you about the theoretical yield, they're saying, what's the maximum amount you can predict? All right? And the maximum amount you can predict is based upon the limiting reagent. So let's take a look at limiting reagents in a chemical problem. 2 grams of this sugar. It's combusted in 2 grams of oxygen, which is the limiting reagent. Now, you can't use mass to make the comparison. You can't even really use moles to compare, because the stoichiometry may not be 1-to-1. In fact, if you balance this equation, C6 H12O6 plus 6O2 goes to 6CO2 plus 6H2O. Let's use this method to predict the amount of CO2 produced. So this is what we're looking with, grams of CO2. So they give us 2 grams of C6H12O6, and our first task is find the limiting reagent. But Dan, how do you know this is a limiting reagent problem? Well, it turns out that you can usually tell a limiting reagent problem because there's a little trick. If they give you more than one reagent, it's probably a limiting reagent problem. A plus B going to C. You have 10 grams of A and 10 grams of B. Usually a limiting reagent problem. So if it gives you more than one reagent, you have to start with the limiting reagent, or else it doesn't work very well. Or else you will get the wrong answer half the time. So we set this up like any other chemistry problem. We predict how much product can form. So we know that given 2 grams of C6H12O6, we can convert that to moles using the molecular weight. So we can use stoichiometry and standard mole to gram conversions. So we can take the grams of C6H12O6 and moles of C6H12O6. And once we have that conversion, we can then use our equation to relate moles of C6H12O6 to moles of CO2. And then from there, we can go from moles of CO2 back into grams of CO2 using the molecular weight. Again, the molecular weight statement, our equation, and our molecular weight. And then we can fill in the numbers from our problem. Again, this aspect is just the molecular weight, so we know that for every 180.2 grams, that's equivalent to 1 mole from the molecular weight of the sugar. Our stoichiometry says that for every 1 mole of C6H12O6, that is equivalent to 6 moles of CO2. And then going back to our equation, for every 1 mole of CO2, 44 grams of CO2 from the molecular weight of CO2. And we can predict how much CO2 would be generated. So generate 2.93 grams of CO2 based upon 2.93 grams of CO2 based upon the C6H12O6. You can set up a similar calculation for the 2 grams of O2. And I'll let you hit pause and then figure out this one yourself. I think it's like right here. Right here. Pause button is right here. So by my calculations, which are always accurate, by my calculations, we would find 2.75 grams of CO2 if we only considered O2. This is based on the sugar. And so the question is, which one is our limiting reagent? Now, this also answers the problem. the limiting reagent is O2, and we can only make, at most, 2.75 grams of CO2. Very typical. So even though we have the same amount by mass, stoichiometry doesn't work out as well in our favor, and so the O2 is the limiting reagent. All right, you can hit stop right now, and you won't miss anything except some cool chemistry in action. So let me introduce an optional method, an alternate way of doing limiting reagent problems. And in fact, it's the one I actually like better because it actually involves thought and understanding. The product method involves just looking at which one makes the least product. The reagent method is an alternate way of doing limiting reagent problems that instead asks the question, rather, how much can I make? It asks the question, how much do I need? So instead of focusing on the products, it focuses on the reagents. How much reagent do I need to make more? Make this much material. Now in the practical setting, out in the lab, this is something we actually do, where we ask ourselves, oh, I got a gram of this material, how much of this other material do I need to complete the reaction? Especially when you're spending top dollar for those compounds, you don't want to be using a whopping excess or too little and waste your material. So the practical side is you ask yourself, how much of this product do I need? So you do the same question here. So you predict how much of other reagent. So rather than ask about the product, I go, okay, I have 2 grams of sugar. How much oxygen do I need to use up all my sugar? So if I have my 2 grams of my sugar, C6H12O6, I would need 2.13 grams of O2. And then we look. Do we have enough? And the answer is no, we don't have enough O2. Therefore, O2 is the limiting reagent. What's nice about this is you only need to do the calculation once. What's not so nice is then you actually have to do the comparison. You have to think about the reaction. On top of that, it doesn't answer the problem. We need 2.13 grams of O2, therefore O2 is limiting. So to answer the problem, we would then have to go back and recalculate our reaction based upon the limiting reagent. So then we'd have to go, okay, we know that the oxygen is limiting. So the limiting reagent is O2. So we know we have 2.0 grams of O2 as the limiting reagent. And then, exactly like our previous example, for every 32 grams of O2, there's 1 mole of O2. For every 6 moles of O2, that is equal to 6 moles of CO2. And for every 1 mole of CO2, that's equal to 44 grams of CO2. Says that we would produce 2.75 grams of CO2 as our product. So now this would be our answer, and this would be our limiting reagent. You're asking yourself, Dan, what's the advantage of this method? Well, 50% of the time you get it right based upon, you get the limiting reagent on 1 try. You don't actually have to do 2 limiting reagent calculations. It's also reagent focused, so rather than looking at the products, if you weren't really caring about the products right away, or you were asked to measure amounts of reaction, then the reagents would be the focus. It's just an alternate method. Whichever way works for you. It works just fine. So those are limiting reagent problems. Find the limiting reagent, use the limiting reagent to answer the problem.